Welcome back, everybody, to the next video. Today, my Apple Pencil is not working, so we're going to have to do this one a little bit raw. But today, we're going to be talking about the Connected-Etale sequence. So first, we're going to have to discuss what a Henselian ring is. So let's say S equals spec R is the spectrum of a Henselian local ring R, such as a field or a complete discrete valuation ring. Those terms have all been defined already in this series of videos. What is a Henselian ring? Well, a local ring R is called Henselian if Hensel's lemma holds in R, essentially. Hensel's lemma from algebraic number theory. That is, a local ring R with residue field kappa, let's say, is Henselian if for every monic polynomial f in R adjoin T and every root A naught in kappa of the reduction f bar of f mod the maximal ideal of R, such that essentially the root isn't repeated. So such that f bar prime of A naught is not 0, where f bar prime is the formal derivative of f bar. There is an A in R such that f of A is 0. And when you reduce A mod the maximal ideal, so when you take A bar, you get A naught. So in other words, to summarize that, non-repeated roots of monic polynomials lift in these rings. That's what's going on here. And a ring R is called strictly Henselian, just for completeness sake, if it's Henselian and it has a separately algebraically closed residue field. You can see Milne's Etale cohomology book, chapter 1, section 4, and also Neukirch, chapter 2, for discussions on Henselian rings. I think also the Stacks project, Columbia's Stacks project, has a nice little write-up on Henselian rings. We'll let M be the maximal ideal of our Henselian local ring R, and we'll let K be R mod M, which is the residue field. And then we'll set S equal to spec K, and that'll be the closed point of S. So because S is spec R, it has a generic point and a closed point, all right? And then we'll just recall that a scheme is normal if all of its stalks are integral domains, which are integrally closed in their fields of fractions. And using much of the material we've developed in previous videos and the discussion above, you can prove the following important facts. We'll call this theorem Theorem 2. This is the Connected-Etale sequence theorem. So let S be as above, and we'll let G be a finite flat S group scheme. So this is the situation we're going to be operating under quite often. Then several things are true. Let's let G0 be the connected component of the identity in G. So G is a group scheme, so that makes sense. Then G0 turns out to be the spectrum of a Henselian local R algebra, and it has the same residue field as R. Okay, so passing to the connected component of the identity doesn't disturb the residue field, so that's nice to know. And it's a flat normal subgroup scheme of G, such that the quotient scheme, and this terminology normal and quotient scheme, I mean those in the sense that were developed this chapter a couple of videos ago. So the quotient scheme, which I'll call G et, which is G mod G0, it's Etale. Et there stands for Etale, okay? And so we have an exact sequence from 0 to G0 to G to G et to 0, and this is called the Connected-Etale sequence for G. So you can essentially take G and kind of kill off a connected piece and always end up with an Etale part remaining. And this sequence has the universal property that every homomorphism from G to an Etale S group scheme factors through the map G to G et, and G0 is the kernel of that map. All right. Okay, what else do we know? What do we know about this sequence? Well, if the residue characteristic of R is 0, then G0 is just S, and G is already Etale. G is just G et. So that's nice to know. Whenever you're working over characteristic R, you just have an Etale group scheme automatically. If this characteristic is prime, so if it's P greater than 0, then the order G0 over S is a power of P. So that's nice to know. Okay, what else do we know? It follows immediately from the previous bullet point that if the order of G over S is invertible in S, then the order of G0 over S must be 1, and G is already Etale. G is just G et. It's Etale over S. And the same is actually true over an arbitrary base scheme because you have this process called Henselization of the local rings. And so I won't get into that, but you can always sort of just Henselize. If R is K, so if R is a field, and if N is the order of G over S, then it turns out G is killed by N. And this is actually an important fact. I think the general proof of this is due to Deligne, and we may talk about it later in the chapter. What I mean by that is x to the n is 1 for all x in G of B for every K algebra B. In fact, more is true though. Like I said, there's a more general result here. A commutative, finite, locally free group scheme over any base scheme is killed by its order in the same way. Okay? And then finally, to end the video, because my pencil's dead, or not working for some reason. If R is a perfect field, so every irreducible polynomial over R has distinct roots. I mean, there's several equivalent, definitions of perfect field. But if R is a perfect field, then the homomorphism from G to G et has a section, i.e. a right inverse. And then, of course, G is then the semi-direct product of G0 with G et. Okay, so next time we'll talk about Cartier duality. And I'll see you then, and thanks for watching.